So now that we've learned about electromagnetism, we can look at some ways that we apply electromagnetism. We'll look at electric motors here. Remember that electromagnetic fields will interact with each other. So here we've got a diagram with a couple of current-carrying wires in between the poles of a permanent magnet. So these are the poles of the permanent magnet right here. Oops, sorry. So these are the poles of the permanent magnet right here. And we've got our wires in the middle, one marked with X, one marked with a dot. So the force on each wire is directed. Let's see what's going to happen here. On the left wire, we'll have a force acting downward, and on the right wire, we'll have a force acting upward. Why is that? Well, remember, if we draw the magnetic field for the permanent magnet, then that will go north to south outside the magnet. So that's in this region here. So those are our magnetic field lines. And if we use our right-hand rule, our third right-hand rule, that means our fingers will go to the right in the diagram to show the direction of the magnetic field. And with the wire on the right-hand side, the dot shows us that the current is coming out of the page, so our thumb points towards us out of the page, and so the force has to be up. On the other wire, we have, again, our fingers point to the right to show the magnetic field direction. The current in this case goes into the page, so our palm is facing downward, so that means the force has to be downward on that wire. And that's what happens with a motor. These wires will spin, but if we just had one loop of wire, that wouldn't give us a lot of force in the motor, so we usually use a solenoid inside. So not surprisingly, a device that uses an electromagnet inside a permanent magnetic field is called an electric motor, and it operates by the motor principle, and that's our third right-hand rule that we talked about. So the motor principle is, well, two magnetic fields interacting with each other. They produce a force, and so the conductor will experience that force and tends to move. As I said, if you use a single wire, in that case, you won't get much force, so we'll usually put a solenoid inside the permanent magnetic field in the motor, and then we get the solenoid to spin and do work for us. We've already talked about the right-hand rule, but there's another diagram to show the force coming out of the palm. It's important that we remember current is shown by the direction of the thumb, and the magnetic field is shown by the direction of the fingers. So the electric motor directs that force, that electric force, full circle. So that means that the wire will spin or the solenoid will spin, and we usually use DC motors. Remember, DC means direct current, which means the current always moves in the same direction. But that means that that current has to have its polarity changed once every rotation. And to do that, we use a split commutator, which is right here. So you'll notice that there's a split, two splits actually, one there and one there. And those splits force that current inside the motor to change direction every half turn. If it doesn't change direction every half turn, then the wire would just stop, because we'd have a north pole attracted to a south pole, and there'd be no reason for it to move unless the polarity of the current switched. We usually use a solenoid, as I said, inside the motor, which really is wire wrapped around an armature, and usually that armature is made from a strong ferromagnetic material like iron. An AC motor is a little bit different. And AC, of course, means alternating current, which means that the current goes back and forth over time. And in North America, that happens 60 times every second. So 60 cycles per second, or 60 hertz, which really means that the motor has to have 60 rotations per second in order to work properly. To get this to happen, we know that the current's going to change direction consistently anyway, so we don't use a split ring commutator. Instead, we use just regular slip rings. So you'll notice that there are no breaks in this ring and no breaks in that ring. And similar to what we saw in the other diagram, we have these connectors called brushes. They're not connected to the rings, but they're just touching them, so the rings are spinning with the wire. You can build a simple DC motor with just a D-cell battery and some wire. That's a little bit tricky. You also need a magnet, a permanent magnet. But if you get a sizable current through the wire, then you can get the wire to spin. If you're making a small motor this way, you probably won't be able to get enough force to get it to do any work for you. But it's a fun activity to see how a motor works. One of the tricks here is to make sure that the wire tails are nice and straight. So when you connect these, make sure they are straight out, or else gravity will play havoc with your spinning armature, which in this case is really just a handmade wire coil. If you're going to try this, it's a good idea to remove some of the insulation from the wire with some sandpaper. Fine sandpaper usually works well if you're going to try that. And so it might look something like this. You don't necessarily have to have a kit. You could probably do this with some homemade materials, but you do need a permanent magnet if you're going to try this. And again, make sure those tails are straight. And copper wire will probably work best. And these connectors are copper as well. And the battery, of course, goes here. If you want to see it in action, you can try this YouTube video. And hopefully yours will work as well if you have time to try it.